Good day, STEM class. We will present today the topic on direct current circuits. Now, there are two types of currents that we will probably encounter. No? One that we call as alternating current, and then another one which we call as direct current. So the direct current circuits are those that uses the battery, whereas the alternating current circuits are those that uses the outlet of our homes. Now, these two are two separate sets of currents because you'll notice that the plug or the outlet where you connect your electric fan, there's no positive or negative end, no, to that plug, like this one, for example. So this is a charger. And we are not worried whether we reverse this when we get it, no, connected to our convenience outlet in our homes. So there's no positive or negative there. So that's what we call as an alternating current. Now, the battery, on the other hand, has a fixed positive and a fixed negative side. So that's a direct current. Now, what we know from our Ohm's law principle, that the current comes out of the positive side of the battery and enters the negative side. So that's how the flow of the current in our circuit. So we will be dealing here with a direct current or DC circuits. And foremost to our understanding here is our idea of Ohm's law. No? So the principle of Ohm's law works in this discussion. So basically, what's Ohm's law? That's voltage equals current times resistance. So we can transform that equation V equals IR, no? I times R, no? Into several forms. Now, we will go into different circuits, and we've discussed this in our capacitances or capacitors about series and parallel connections. And we'll begin today now with series connection. So let's take the series connected circuit. No? So instead of an actual resistor, what we use here is our two bulbs, light bulbs. No? But we consider this as resistances because inside the bulb, no, inside this glass in the bulb, is a coil of wire that has a very high resistance. The reason we call it to have a high resistance because this one glows when heated, no, until it eventually, no, produces light. So it is producing, no, some sort of a heat and light, no, as an effect of the resistance there. No? Now again, no, a resistor looks a bit different from this, but since they have resistances, then we can consider this as resistors as well. Now, the way the resistors or the bulbs are connected, they are connected, no, from one terminal to the next device, no, and therefore we end up with a series connection here. No? Now, the way we know that this is series is that when we detach one bulb, the whole circuit will no longer function. Now, from our simplified expression here or diagram, no, our schematic diagram on the other end, we will only see that there's only one resistor here, no, or resistance. So therefore, what happens there is that we combine these two resistances and eventually call it as Req, or the equivalent resistance. So the equivalent resistance may be thought of, no, as something like a total resistance. No? So therefore, no, you can add together the values, and therefore no, you end up with only a single value. No? How you come up with that value will probably largely depend, no, on it will depend on the kind of circuit that we have. No? So once we simplified or combine these resistances, we can simply look at, no, if there's a battery here and a resistance, then a simple expression of the Ohm's law can be used to relate I, R, and V. No? Now, going back to series connection, now what are the things that we can see here now if we have a series connected devices? So let's look at series connected devices. We have series connected resistances, no, in this case. So what if we have no series connected resistances? No? So what will be, no, the thing that we have here? Now, so first of all, what we will see there is that, no, the very first relationship probably that I will mention is that the total current that comes from the battery is eventually simply being passed on from one device to the next. So if I assume that there are three resistors there, so I will end up with I1, I2, and I3. But you see there that there's only two bulbs. So we could probably settle with I1 and I2. But so, let's say there are more. Now what we will notice is that we will have here equal values for our current whenever the resistances are connected in series. However, as this current passes the first bulb, a voltage will result. So there is already a voltage on the battery, but as I1 passes resistance 1, then V1 will result. Likewise, V2 will also result as a product of current and resistance. But what's the relationship of the voltages here? Are they also equal to each other? Now again, what they found in series connection is that when you add up these voltages together, it's equal to the voltage of the battery. So this is how the voltages work. So that's the second principle. So the first principle, that the currents are all equal, while the voltages in each resistance that we can probably call as voltage drop. When you add them up, it's equal to the voltage supplied by our battery. Now the third one is with regards to the total resistance. The total resistance is in terms of the individual resistances are 1, R2, R3 probably, if there are 3 of them. And their total value is simply to add them up. Now this is true only when you deal with series connected resistances. And we can actually see that over here. So that principle is the same as the one I just wrote. So there are 3 concepts that we can follow whenever we deal with series connection. Now, on this end, on the right side, this is vastly different from the series connection because if you try to examine this, this is a parallel connected resistances or bulbs. And the thing about these parallel connected bulbs is that when we remove one bulb, like the one at the top, the circuit will still have currents that is able to flow in the circuit. So let's say removing R1, you'll notice that the current will simply pass through the resistance number 2 or bulb number 2, and still complete a path. But in series connection, if you remove one of the bulbs here, the flow of the current is eventually cut. So the bulbs will no longer function, even though you only remove one of them. But not in parallel connection. Parallel connection, the current will simply pass through another path whenever you remove one of the connected device in parallel. Now let's look at the parallel connected devices, and let's summarize what are the things that we can see here. So parallel connected resistances. The first one again is in terms of the voltage. So the total voltage in our circuit is equal to each other. So V1, V2, and V3. They are equal to each other. Now, for our other characteristics, now the current here, on the other hand, so current total from the battery is now being added to one another. So, amo na yung gina-add natin. So, the currents are the ones that are being added together. And finally, the last principle here is that the value of our total resistance is the reciprocal of the individual resistance. So the reciprocal of the total resistance is equals to 1 over R1 plus 1 over R sub 2. And that's equals to 1 over R sub 3. If there are only 3 resistances there. If there are more, then we can add succeedingly. Now again, if you can remember this, so this one has a resemblance to our concept in in capacitance. No? So, however, this reciprocal expression, we write this when we deal with our our series. I think that was a series capacitances. No? So for our series capacitances, then we have to get the reciprocal value to get the total capacitance. No? So again, that expression is also shown below. No? So the 1 over the equivalent resistance is equals to 1 over R1 plus 1 over R sub 2 plus the succeeding reciprocals of the succeeding resistances. Now, in summary, we can see that one in the next slide. So in our next slide, let me erase this. So let me delete that. No? So this is now our summary of our resistances, no? The different connections in our resistances. And as an example, no, we will try an example here. No? Let's say we will find the following values. No? So first we'll start with series connection. I think among the values that we can easily calculate here is the total resistance RT. No? So in series connection, to get the total resistance, we simply add all the individual resistances. No? So if there are 3 of them, then we add simply these values. No? And our answer there will be around 84 ohms. No? Okay. Now, next, probably after getting our total, no, we can also next solve our I3. No? So the current that passes resistance 3 is also equal to the current that comes from our battery. No? And that's equals to Vt over R sub T. No? So that's Ohm's law principle. No? So the current that comes from the battery is eventually equals to I1, I2, and I3. No? So therefore, we can simply equate this one. No? And therefore, if you'll try to calculate I3, so if Vt is given to be 8 volts, no? So there's a value there, 8 volts. So if you check this round with plus and minus sign, this is the battery. So this is our Vt value. No? So that's 8 volts. So if you divide that 8 volts value by 84 ohms, then we will roughly have a value that's around, I think, 0.095, and that's in current, therefore that's in amperes. Okay, so what are the things that we've calculated so far? So RT, so this is our R sub T. Our I sub 3 is already known. So there's one last value that we will calculate. Now, if we will try to solve for V sub 2, V2, calculating V sub 2 will be equal to I2 times R2. So do we know I sub 2? No? Again, we know it because it's equal to our value earlier. No? That's equivalent to the total current. No? Now, if our R2 is 50 ohms, and therefore the product there gives you now your number of volts. So that's equivalent to, so that's 50 times 0.095. So that's 4.75. Okay, so we've calculated already the 3 values of our circuit. Okay, now we go on to our next figure. Okay, continuing. So we are now on parallel connected resistances. So we are given, instead of R1, R2, and R3, we kind of skip R3 and we have R4 instead. But there are only 3 resistances here. Now, from our 3 resistances, we will have here a current that comes from our battery, And that current that comes from the battery is eventually passed on or split into three different resistances. No? So that's your R2, this is your R4, this is your R1. So therefore, this is your I1, I4, and I2. No? So these three values are the ones that you add up together, and that's equivalent to the current that is coming from our battery. No? So the one that comes from our battery is known as our I sub T. No? Now, what is noticeable in our parallel connection is that if you'll try to calculate this value now, no? Our solution, no? I think the first one that we can solve is our V sub 2. No? Why V sub 2? Because V sub 2 is equal to V total. No? So any device that we connect in parallel, their voltages are all equal. So therefore, V2 must be equivalent to 12 volts as well. No? So we did not solve that anymore because we know by principle that that's equal to 12 volts. Now, the next value probably that we can think of is the value of I1. And how do we get I1? That's using Ohm's law. We have V1 divided by R1. And if we try to look at the value, V1 is 12 volts. And we divide that with I1, which is 16 ohms. So if we'll try to divide 12 by 16, then we'll have 0.75. That's 0.75. And that's in amperes. No? Okay, so we already calculated two of them. No? Now the last value is the total resistance. And we can get that by getting the reciprocal value. So we have our reciprocal value there. So we will have three values there. No? So R1, R2, and R4. And in this case, we will end up with 1/16. And then we have 1/10. No? That's R2. And R4 is 24. So 1/24. No? And I think now by using your fraction, the value eventually of 1/R sub T is 49. No? Divide by 240. No? So that's not the value of RT. No? If we add the fractions 1/16, 1/10, 1/24, which equals to 49/240. But when we want to get the total resistance, then we will get the reciprocal of 240 and divide it with 49. No? And R sub T, therefore, will be equivalent to 240 divided by 49. Then we will have 4.9. No? More or less, if we round that off, no, that's 4.9 ohms. No? Okay, so that's our total resistance. So we were able to get the three values that we want to determine. No? Okay, so again, we use the concept of the reciprocal over here. We use the concept of Ohm's law, and the concept of parallel circuits where the voltages are equal in finding the current, and likewise voltage. No? We also use the principle of parallel connection where the voltages are simply equivalent to each other. No? Okay, so this is our example for parallel connection. Now, let's have some analysis, a bit of an analysis. Now, imagine if instead of connecting this in parallel, what if we connect them in series? What will happen to the total resistance? No? Will the total resistance increase or will it remain 4.9 ohms? Again, if we will deal with series connection, if we add up all these values, then I think 16 plus 24 plus 10 will give you 50 ohms. That is way too high, that's 10 times higher than 4.9, roughly. a little more than 10 times. No? So therefore, no, in series connection, what happens is that the total resistance actually increase. And if we base that with Ohm's law, once the resistance increases, the current will eventually decrease. So they have an inverse relationship here. So therefore, if we will try to analyze no parallel connection on the other hand, as we connect resistances in parallel, then there's a tendency that the total resistance will get lesser or lower and lower. And probably if you add more devices there in parallel, it will eventually result to a lesser value of resistance. And therefore, if the resistance decreases, there's a possibility that the current there will increase no, as you add more and more devices. So the point that I'm driving there is, if you are fond of using no, an electrical wire, no, like an extension cord, no, and in that extension cord, there are so many outlets there where you can plug no, several devices. You are advised no, not to extend no, or plug so many more. No? Okay? Because again, no, it will increase the current, and the wire that you are using in your extension cord has a limit. Once that limit is exceeded, the wire will heat up or it will get burned. No? So our wirings have a maximum value. So therefore, no, to avoid hazards like fire, no, sunog ka mo, then think about no, the capacity that the wire can carry. No? Okay, now at this point, now you are to make your seat work. No? And for your seat work, I want you to answer this next slide over here. No? But I'm going to erase this one first. No? So let me erase this. And here is our diagram no? For our next activity. And you are to answer no? The different parts of this activity. Okay, at this point now, you are given or shown no? A series parallel combination. And for you to answer this seat work, no? I want you to probably no analyze this. No, how are these two resistances here? No, R2 and R3 connected. How are they connected? Are they in series or are they in parallel? No? So again, the way you answer that is by removing the device, one of them. If you remove one of them and the circuit still no, allows current to flow, then that is what we call a parallel connection. However, now if you try to remove R1 on the other hand, this 80 ohms resistance, and if the circuit cannot allow current to pass anymore once you remove this, then this is somehow in series to the battery and in series to these two. No? So again, no? If they are behaving like series connected device, then you can apply the series connection principles. No? But if they are connected in parallel, then you are to apply no? The parallel connected principle. No? So it depends. No? So therefore, now these are the things that you will answer. Now, at the end of the class period, no, you are to submit this no, submit in groups of 3 or 4. Okay, 3 or 4, and submit this in my email. Do not forget to include the names of your members. So submit that in this email address, and then label the activity as series parallel combination. So write that as the subject of the email. And likewise, when you are done with this, now you may also discuss with your group or finish. You may finish the lab presentation 3, which is due tomorrow. So please don't forget to finish your lab presentation. So you will group yourselves by Einstein groupings. No? But however, the submission will be done in groups of 3 or 4. So leaders, please gather your members and work on this activity. No? So for today. No? Okay, so I think you understand that, no? And hoping, no, to see your work, no, at the end of the class period.